Hello everybody, this is week 7. Today we will study lattice Boltzmann models to simulate the motion of particles in fluid substances. Last week we introduced lattice gas model or LGM to simulate fluid dynamics. We discussed two models, HPP and FHP, to simulate the kinetics of particles in gases and liquids. As explained, these two models simulate gas and liquid motions based on two-dimensional cellular automata. This week, we are going to study the lattice Boltzmann model or LBM as another solution to the fluid dynamics problem. In LBM, the flow of fluids is modeled based on the statistical mechanics of particles in the gas and liquid substances. In other words, in the lattice Boltzmann model, we use probability distribution functions to characterize a fluid substance. As discussed last week, the Navier-Stokes equation mathematically characterizes fluid substances by a set of parameters such as density and velocity. These parameters are defined as functions of position and also depends on time. For instance, the parameter ρ determines the density of a point located at a position x and y in a given time t. In the 1870s, Boltzmann introduced another model for complex fluid systems. In this approach, a single function f represents the probability or distribution of particles in fluid substances. As we can see here, f is a probability function of two vectors, position and velocity. X and Y represent the position of an individual particle in a fluid substance. Vx and Vy correspond to the velocity state of the particle. In other words, the function f characterizes the probability that a particle may be at position x and y with the velocities Vx and Vy. This slide presents the Boltzmann equation. As shown here, this equation characterizes a fluid substance based on the probability function f, velocity v, and the collision operator function omega. In this equation, f and v are functions of position. Like Navier-Stokes, this equation involves some partial derivatives that make it complicated to solve this equation using binary computers. To solve the Boltzmann equation by computer, we need to mathematically discretize the partial differential equations, which demands lots of mathematical effort. To address this problem, last week we used HPP and FHP models based on the lattice gas model and cellular automata. If you remember, in these models, the velocity state of each particle in each cell was discretized using a Boolean array named flock. Each component in this array had a certain value, 0 or 1. We can adapt the same notion to characterize the position and velocity of each particle in the Boltzmann model. However, it should be noted that f is a probability function and its range is continuous instead of 0 or 1. Based on the theoretical discussion on the previous slide, I have listed two main steps that should be taken for generalizing a lattice gas model to a lattice Boltzmann model. In the first step, we should generalize the state array flock. If you remember, flock models the local cell state of cells in a lattice gas model using a set of Boolean variables. Since the probability function f in the lattice Boltzmann model has a continuous range, we should generalize the array f to taking floating point values rather than Booleans. These floating point values determine the expected number of particles in that state. In addition, we should modify the collision rules in lattice gas models considering the probability function f. Now, we want to discretize position and velocity in Boltzmann equation. There are different approaches to implement the lattice Boltzmann model. One approach simulates gas and liquid motions based on a two-dimensional cellular automaton. The grid is populated by a set of particles with 9 different velocities or states. As shown here, C0 represents a particle with 0 velocity. C1 a particle or a vector moving from the left to the right, and so on. This lattice is named D2Q9 velocity state because of using a two-dimensional grid with 9 states. We can also simulate the lattice Boltzmann model using a cubic grid with 19 velocity states. This model is called D3Q19, as illustrated here. In the previous slide, the position and velocity of particles were discretized using two different velocity states, D2Q9 and D3Q19. Generally speaking, the velocity states can be represented by a set of Q vectors. Q is commonly referred to as a state Ci, where I ranges from 0 to Q-1. And each vector can be d-dimensional. For instance, in the previous slides, d was 2 and 3 respectively. Based on the discrete velocity states discussed in the previous slide, Boltzmann's distribution function f can now be given in its discrete form. Like the lattice gas model, the discrete distribution function f can be modeled using a vector. For instance, here we have a vector modeling the cell state array in D2Q9. Each cell in the vector represents a state, and its value determines the probability or the expected number of particles in that state. As mentioned in the previous slide, array f determines the local state of each cell in the grid. Based on this, the local density of a cell located in a position x and y is defined as the summation of all components in its local state array f. In this formula, f x, y represents the state array of a cell located in position x and y in a two-dimensional grid. We can also obtain the local velocity of a cell as a weighted average of discrete microscopic velocities. In this series, Ci is a constant value. In the lattice Boltzmann model, like the lattice gas model, we have two steps for computing the next generation of cell states. Using these rules, we can simulate the motion of particles in a grid. The first rule is collision, followed by the streaming step. Both steps of rules must be applied to any cell in a grid in order to compute the next generation of cell states. It's interesting to note that the streaming step in LBM is essentially identical to that in a lattice gas model. So, based on the streaming rule, a distribution component fi x, y with velocity in a particular direction at a particular cell is copied one place to the next cell in that direction. Please note that the state C0 or the zero velocity component remains unaffected by the streaming rule. In the LGM, we considered all possible collisions of individual particles to obtain collision rules. But in the LBM, the collision is approximated using the formula presented here. In this equation, f in x, y is the distribution function before the collision step, while f out x, y represents the distribution after the collision. Tau is a constant parameter related to the desired viscosity of the simulated fluid. In the collision formulation, we use the distribute function f eq x, y as defined here. F eqi is a function of density ρ and velocity u. Vi and cs are constant values that depend on the velocity states. Okay, we have enough information to simulate the realistic flow of a two-dimensional fluid using the lattice Boltzmann model. However, we haven't yet discussed matters such as choosing initial conditions and boundary conditions. We might return to these matters next week. That brings us to the end of today's lecture. Thanks for watching this video.